Realistic.
And let me see, for those of you out there in Zoom, let me see if I have published chapter 11. Oh, I didn't. So let me do that now.
Yeah, I don't know where my. Calculator.
Okay, so let me go here, share my screen. And maybe do it here. Chapter 11. All right, so you said we got to question number
Right.
3?
Yeah.
Okay, so just to remind you, the equations that we're using for this topic is C is equal to lambda times nu. C is the speed of light, lambda is the wavelength, and nu is the frequency. So let's see, this question says radar signals are electromagnetic radiation in the microwave region of the spectrum. Typical radar has a wavelength of 3.19 centimeters. What is the frequency? So basically, you have to rearrange this to get nu, which is equal to C over lambda, right? So remember, C is always equal to what? 3.00 times 10 to the 8 meters per second, right? So 3.00 times 10 to the 8 meters per second, that would be the C divided by the wavelength, which is 3.19 centimeters. But we have to convert this to what?
Meters.
Exactly. So we multiply by 1 meter above divided by 100 centimeters below. And that's the setup. So let's see here. 3 times 10 to the 8 divided by 3.19 times 10 to the minus 2. And according to my calculation, so I got, rounded off to 3 sig figs, I got 9.40 times 10 to the 9. And the units here would be hertz. That's how I would do that. Okay, any questions about this one?
No.
Questions? All right, so let me clear this. Scroll down. Okay. Number 5. How would you deal with this one? Let me hear some ideas. How would you do number 5? The question is asking for the wavelength.
Oh, wait.
So
Oh, understood. Would be C.
C is equal to lambda times nu, right? Okay. But the question is asking for lambda, the wavelength. So lambda would be equal to what?
Oh. I mean, it'll be equal to
C over nu, exactly. So 3.00 times 10 to the 8 meters per second divided by the frequency, which is given as 3.76 times 10 to the 14 seconds to the minus 1. So let's do here 3 times 10 to the 8 divided by 3.76 times 10 to the 14. And according to my calculation, this works out to be equal to 7.98 times 10 to the minus 7. And the units here would be meters. All right. Okay, any question about this one? All right, so this, 1 minute. based on what we have just done, you should be able to do the rest in this section here. So, put this here. So you should be able to do the rest from number 6 all the way down to number 14. Now, let me just say this. In the case of number 12, there's this unit here. I don't think I mentioned it in the video, so let me talk about it now. It's called the Angstrom unit, where you have an A with a small O at the top. It's called the Angstrom unit, right? And it's not a metric unit, but it's related to it. 1 angstrom would be equal to 10 to the minus 10 meters, all right? So you're going to need that information in order to solve that problem, all right? But the rest of them you should be able to do, all right? Okay, so let me scroll down. Let me clear this first. And let me scroll down to the B part. Now, the B part has to do with what is called the electronic configuration, right? And I went into a discussion of that. Basically, for atoms, our current modern understanding of how the electrons are arranged in the atom is that in the atom, you have what are known as energy levels, also known as shells. And within each shell, you have a certain number of what we call sublevels. And within each sublevel, you have a given number of orbitals, right? Orbitals are basically regions in space where the probability of finding an electron is very high, right? And different sublevels will have different numbers of orbitals within those sublevels, right? So, and then another thing you have to take into consideration is the relative energies of those sublevels, right? And there's a diagram which is in the PowerPoint. Let me see if I can find the PowerPoint, which you need to memorize. Well, before we get to the diagram, I want to point out that, as I said before, you have the sublevels, and within each sublevel, you have the orbitals, right? And this diagram here basically summarizes the number of different types of orbitals present within each sublevel. So in the first shell, right, you have only one sublevel, that's called the 1s sublevel. And within that 1s sublevel, there's only one orbital, right? So therefore, you have only one s orbital present in that n equal 1 shell. In the n equal 2 shell, you have two sublevels. You have the 2s and the 2p's, right? There's only one s orbital in that sublevel, but as far as the p orbitals are concerned, there are 3 of them, all right? And then in the third shell, you have the s sublevel, the p sublevel, and the d sublevel. And the number of s orbitals would be 3, the number of p orbitals would be, I'm sorry, the number of s orbitals would be 1, the number of p orbitals would be 3, and then there are 5 3d orbitals. And then when you get to n equal 4, the fourth shell, you have 4 sublevels, you have 4s, 4p, 4d, and 4f. There's only one 4s orbital present in the 4s sublevel. There are 3 4p orbitals in the 4p sublevel, 5 4d orbitals in the 4d sublevel, and 7 4f orbitals in the 4f sublevel, right? So you need to keep these numbers in mind in terms of the number of orbitals within each sublevel. Another thing I should mention too is that each orbital can have a maximum of 2 electrons, right? So you can have no electrons, 1 electron, or 2 electrons, but no more than 2 electrons within each sublevel. And if you have 2 electrons within each sublevel, then those 2 electrons, while occupying that 2p orbital, must be spinning in opposite directions. And there's some diagrams that I think I have here. Let's see if I can find it, which shows you how the electrons are distributed. Okay, like, so basically, Hydrogen is the simplest atom. It has only one electron. That one electron will go into the lowest sublevel, which would be the 1s sublevel. Then the next element would be helium, which has 2 electrons. Those 2 electrons will go into the 1s sublevel. That sublevel is full because it only has 1 orbital, and the maximum capacity of any orbital is 2, right? So once you get to that level and you're trying to find out the electron configuration of the next atom, then basically you're going to end up with lithium. In the case of lithium, you're going to have 2 electrons in the 1s sublevel, and therefore the next electron can only go into the next higher sublevel, and therefore this will be the electronic configuration of lithium. And by the way, this is another way of writing it: 1s2, 2s1, right? And then if you go to the next element, beryllium, you have 1s2, 2s2, right? And so on and so forth. So that's basically how you can determine the electron configuration. So this begs the question: how do we know the actual order of these sublevels? And that's the diagram I'm trying to get to right now, which you need to memorize, which is oh, here it is, right? So this diagram is what you're going to use to help you to determine the order of the energies, order of the orbitals, I should say, in terms, or the sublevels in terms of your energies, right? When I was a student, what I would do to remember this is I'll take a sheet of paper and then I'll write down to the left side 1s, 2s, 3s, all the way down to 7s. And then the next column will start with 2p all the way down to 7p. And then the next column will start with 3d all the way down to 7d, and so on and so forth, right? So once you do that, then what you do next is draw the arrows, as you can see here, right? And then to establish the orders, you follow the arrow starting from the 1s here, from tail to head, right? So the order of the energies of the orbital will be 1s, then 2s, then 2p, then 3s, then 3p. So all I'm doing is follow the arrows and where they intersect with the different letters. 3p, then 4s, then 3d, and so on, right? So basically, once you do that, then you pretty much can determine the order of the orbitals, and therefore, based on that, you can determine the energy, or I should say the electron configuration of a particular atom, all right? So for example, if you're asked to write down the electron configuration of nitrogen, right? The first thing I would do is go to the periodic table, and I would look up the atomic number of nitrogen, which is 7, right? So that means that you're going to have 7 electrons that you need to indicate in the electron configuration. So the first sublevel will have 2 electrons, that's the maximum capacity. And then the next sublevel, which will be 2s, will be occupied by 2 electrons. The next sublevel will be 2p, right? Remember now there are 3p orbitals, right? So therefore, the remaining 3 electrons will simply go into the 2p sublevel. And that would be the electron configuration of nitrogen. 1s2, 2s2, 2p3. And that's it. All right. Another thing I should mention, and that means I have to scroll up to the top here. I should mention that there is 2 ways of expressing the electronic configuration. One is called the full electronic configuration. I think in your assignment, it's called the standard. Let's see here. I think it's
unabbreviated.
The unabbreviated, right? Same thing, right? The unabbreviated electron configuration is basically what I just described, right? And I think I have some examples here. So in the case of boron, if I were to write down the unabbreviated or full electronic configuration of boron, that would be 1s2, 2s2, 2p1. Now, in some cases, as you can imagine, when you get to the larger atoms like silver and platinum and so on, you can imagine the number of characters there would be much longer, right? And in some cases, you don't need that much information. So therefore, there's an abbreviated version which would suit just fine in some situations, right? So what I'm going to show you is how do we get from the full electron configuration to the abbreviated version using the boron example. So this is the full electron configuration of boron. if I were to write down the abbreviated version, what I would do first is look for the group 8 element that immediately precedes boron. So boron is there, right? In atomic number 5, the group 8 element that comes before boron is helium, right? Helium has the electronic configuration, which is colored blue right here, right? So therefore, to get the abbreviated version from the unabbreviated version, you replace the electron configuration of helium in this configuration here with the symbol of helium in square parentheses. And then you write down the rest of it, which would be 2s2, 2p1, all right? So this would be the full or unabbreviated version, and this would be the abbreviated electronic configuration of boron. Now, admittedly, there's not much difference between these two in terms of the length of characters, right? But what you're going to see is that for larger atoms, let me see if I have an example here, like sodium, right? If I were to write down the full electronic configuration of sodium, this is it, right? So to get, as I said before, to get from the full electron configuration to the abbreviated version, what I will do first is consult the periodic table and look up the group 8 element that precedes sodium. So sodium is there, atomic number 11, right? So the group 8 element that immediately comes before sodium is neon, right? And neon will have this right here as the electronic configuration, right? So basically, to get from the unabbreviated version of sodium in terms of the configuration to the abbreviated version, you're going to replace all of this here with the symbol of neon in square parentheses, and then you write down the rest after that. So here you can see the clear difference in terms of the number of characters needed in order to get the abbreviated version from the unabbreviated version, right? So I think I have another example lined up. Chlorine, right? So the full electronic configuration of chlorine is this right here, right? So again, we consult the periodic table and we look up the group 8 element that comes before chlorine, which is going to be neon, right? So it's the same electronic configuration that we have here, as well, right? So basically all of this will be replaced by the electronic configuration of neon, which is this right here. And then we write down the rest, which is this right here. And that would represent the abbreviated version, the abbreviated electronic configuration of chlorine. Okay, so with that said, going to the assignment, in fact, we just put this up on the screen. Okay, so part B, the first part of part B, is asking for you to write the unabbreviated electron configurations of the following elements. And I think we just did sodium and chlorine already, but let's write it down again. So remember, in order for you to write down the electronic configuration, you're going to need this table right here. Oops, sorry, not that table. This table, this chart, right? So let me see if I can do a little split screen kind of thing. Okay, so we're going to use the chart here to get the full electronic configuration in the case of sodium. So in the case of sodium, the first thing you do, of course, is go to the periodic table, look up the atomic number of sodium, which is 11, right? So we have 11 electrons to play with. So it would be the first two electrons, what am I doing? The first two electrons will go into the 1s sublevel, 1s2. Then the next two electrons will go into the 2s sublevel. So we're going according to this. Then 2p. Now p sublevel, the maximum capacity is 6, right? And then the next sublevel will be 3s, and therefore the remaining electron will end up there. And that would be the full electronic configuration of the sodium atom. All right? Any questions about this? Any questions? Yes, sir.
How do you know like what the maximum capacity?
Good question. Goes back to this chart which I showed you earlier. Where is it? Oh, here it is. Okay, remember this chart, I'll show you, right? The key thing you need to remember is that each orbital can have a maximum of 2 electrons, right? So in the case of the first sublevel here, you have only a 1s orbital, so the maximum capacity there is 2, right? In this case here, same thing for the 2s orbital. But because you have 3 2p orbitals, within that sublevel, the maximum capacity is 6. Because you have 3 2p orbitals, each of them can have 2 electrons. And then when you get to the 3d sublevel, the maximum capacity will be 10.
Okay.
All right, and then when you get to the 4s sublevel, the maximum capacity is 14. Right? So it's 2 4s, 6 4p, 10 4d, and 14 4f.
Okay, so basically 2 times.
Exactly, right, exactly. Okay, so let me find back that chart. Okay, so that's the chart we're going to use. Okay, so in the case of chlorine, again, we consult the periodic table and we see that chlorine has an atomic number of 17, right? So the first 2 electrons will go into the 1s sublevel, then 2s2, then 2p6, then 3s2, all right? And then the next sublevel will be the p sublevel for 3p. So therefore, the remaining 5 electrons would end up in that sublevel, and that would be the electronic configuration of chlorine. All right? Okay, so since I've done the first 2 for you, how will you do number 3? Magnesium, what's the first thing you look for? Oh, okay, your atomic number is 12. All right. So the first 2 electrons will go into the,
So that 1s2.
1s2, right? And then
2s2.
2s2, and then, oops,
2p6.
2p6, and then,
Oh,
3s2.
nope.
three.
Oh, yeah, 3s2. All right, yeah, you're right. And that's it. All right. What about nitrogen? What's the atomic number of nitrogen?
7.
7. So, first sublevel will have 2 electrons, and then
2s2.
2s2, and then, oops, s. Hold on, 2s2, and then 2p3. Okay, very good. What about silica? What's the atomic number of 14? Okay, so silicon is 14. So tell me what to write down.
1s2.
1s2,
2s2.
2s2,
2p6.
2p6,
3s2.
3s2,
2.
3p2. 3p2. Okay, very good. All right, and that's it. All right. Now the second part is asking for the abbreviated version. So what I would do, I would write down first the full electronic configuration first, and then from there figure out what the abbreviated version is, right? So let's start off with aluminum, which has an atomic number of 13, right? So the full electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p1, right? That would be the electronic configuration of aluminum. Now, if you remember what I said, to get from the full to the abbreviated, we go and look at the group 8 element that immediately comes before aluminum. So aluminum is there. The group 8 element that comes before aluminum is neon. Neon has 10 electrons, which would be this part right here. Right? This part I'm circling for the aluminum configuration would have the same electronic configuration as neon. So basically, to get this abbreviated version, you're going to replace this with the symbol of neon within square parentheses, and then 3s2, 3p1. And that's it. That's how you get the abbreviated electron configuration of neon. All right. Okay, any question about that one? Any question? Okay, what would you say about carbon? What's the atomic number of carbon? Yes, sir.
6.
Okay, so the atomic number, what is this? 1. Okay, So the atomic number of carbon is 6. Okay, so let's do the full electronic configuration first. So what should I write down?
1s2,
1s2,
2s2,
2s2,
2p2.
2p2. Okay, so how would I go from here to the abbreviated version?
Helium,
Helium in square parentheses followed by
2s2,
2s2,
2p2.
2p2. Exactly. That's it. All right. Any question about that one? Any question? Okay, fluorine. What's the atomic number of fluorine?
9.
9. All right. So let's do the full electron configuration first.
1s2,
1s2,
2s2,
2s2,
2p6,
2p6,
3s1.
3s. Hold on, wait a minute. Fluorine.
Or sorry, it's 1s2, 2s2, 2p5.
2p5. Yeah, do something with that. Yeah. So this should be 5. Okay, very good. So how do we get from here to the abbreviated electron configuration? Helium again would be the group 8 element. And then we follow that up with what?
2s2,
2s2,
2p5.
2p5. Very good. Okay, phosphorus. Okay, phosphorus. 15 is the atomic number. Right? So what should I write down here? Let's start off with the full.
1s2,
1s2,
2s2,
2s2,
2p6,
2p6,
3s2,
3s2,
3p3.
3p3. Exactly. So what's a group 8 element that precedes phosphorus?
Neon,
Neon, right? So neon will take care of all of this right here I'm circling. Right? So therefore, we put neon symbol in square parentheses followed by what?
3s2,
3s2,
3p3.
3p3. Exactly. Okay. And then the last one in this series is boron. Boron is 5, right? So what's the full electron configuration of boron?
1s2,
1s2,
2s2,
2s2, 2p1. So what would be the abbreviated version?
the helium,
11 square parentheses followed by
2s2,
2s2,
2p1.
2p1. Okay, very good. All right, so that's basically how that is done. Okay, any questions about it? Any questions? So remember, you need to memorize this here, right? In order for you to be able to answer that type of question. All right, let me clear this. And let's scroll down. Oh, some more. Okay. Some more electron configuration. All right, so let's do, you know what? I'm going to leave you guys to do that one. Do those. You should be able to do those. All right, so make sure you do those. If you have any questions, of course, please come and see me or call me or whatever. We can communicate on Zoom as well. Okay, so let's get to this chart here that we need to complete. So basically, you just need to fill in the spaces based on the information given. And the first one is shown as an example. So let me just go through that example and we can look at the others. So oxygen, atomic number 8, you can get that directly from the periodic table. And then the number of electrons in each energy level or shell. So of course, we know that the shells are the energy levels. The first shell can have a maximum of 2 electrons. The second shell will have a maximum of 6. And then the full electronic configuration, we just did some exercise with that. And then now, to get the number of electrons that is probably lost or gained, basically what this is dealing with is situations where an atom will either lose or gain an electron to obtain a full outer shell, right? Now, metals typically will lose electrons and non-metals will typically gain electrons. In either case, they will either lose or gain electrons to end up with a full outer shell. So in the case of oxygen, the outer shell here has 6 electrons. The maximum capacity would be 8 because you have 2 for the maximum capacity of the S and 6 for the maximum capacity of the piece of metal. So therefore, that's why it says here gain 2. So when it gains 2 electrons, then the number of electrons that would be either left or gained, or after the loss or gain would be 10. And in terms of the charges, or the charge on the ion, basically, if it gains electrons, it will basically end up with a negative charge. If it loses electrons, it ends up with a plus charge. The actual magnitude of the charge is dependent on the number of electrons lost or gained. So in this case here, because it gains 2 electrons, then the charge on the resulting ion will be -2. So with that said, let's see if you can complete the second row. Sodium is that element. What's the atomic number of sodium? 11, right? So what would be the number of electrons in each shell?
Would be
So the first shell will have how many?
2.
2. The next shell will have how many?
6. 8.
8. And then the third shell will have?
3.
Nope. 1. Because remember, this must add up to give you 11. All right? Okay. Now, what would be the full electron configuration? So you're going to need that chart to help you, right? So you may want to pull it up. In fact, let's see if I can pull it up. Okay, so let me redo this here. Okay, so this is 11. This is 2, 8, 1. And then here is what now? What's the electron configuration? 1s2, 2s2,
6.
2p6,
3.
3s1. Very good. Okay. Now, what's the number of electrons lost or gained in this case? Remember what I said, metals tend to lose electrons, non-metals tend to gain electrons.
Would be 8.
Sodium,
It would gain 1.
nope,
Would it lose 1?
it's gonna lose 1. Right? It's gonna lose this one right here. All right? So what will be the number of electrons left after the gain or loss? 10. So what will be the charge?
-1 plus 1.
It loses an electron.
Plus 1.
Oh, plus 1. Yeah. All right? Okay. What about sulfur? What's the atomic number of sulfur?
16.
16. Okay, what would be the number of electrons in each of the energy levels?
2.
2,
8.
8,
6.
6. Okay, very good. What would be the full electron configuration?
4s2.
1s2,
2s2.
2s2,
2p6.
2p6,
3s2.
2p6, 3s2,
3p4.
3p4. Very good. All right. So that would be the full electronic configuration. Now the next question is, how many electrons will be lost or gained by sulfur to get a full outer shell?
18.
It's going to gain 2. Gain 2. So therefore, the number of electrons after that would be what?
18.
18. And what will be the charge?
-2.
It's 2. Okay, very good. So based on that, I'm very confident you should be able to complete the rest of this table. It just follows the same idea as in the example that we just looked at. Okay, so what I'm going to do is clear this. And scroll down. Okay, so now we're going to get into a discussion of trend in the periodic table as you go across a period and down the group, right? And if you watch the videos, then we talked about in the videos changes in the sizes of the atoms, right? As you go across a period and down the group. And I think we also discussed changes in the ionization energy or electronegativity. Let's see. Okay, so let me start off with a discussion of atomic size, right? So basically, when it comes to atomic size, there are different things that will be happening as you go from left to right of any period or going down any group. So let me talk about going from left to right of any period. What you're going to find is that as you go from left to right of any period, there are two changes taking place, right? One is you're adding a proton to the nucleus, right? So as you go from, let's say, period 2, as you go from lithium to beryllium, boron, and carbon, and so on, you're adding a proton to the nucleus, right? At the same time, you're adding an electron to the same shell, right? So what's the consequence of that? The consequence of that is that because you're adding protons as you go from one atom to the next across a period, you're increasing the nuclear charge, and the nucleus will have a greater pull on the surrounding electrons, right? And therefore, as a result, the atom is going to shrink as you go from left to right of any period, right? So basically, period 2. Lithium, if you look at that series in that row, of that row, lithium will have the largest size, right? And then the size will decrease to going to beryllium and then boron, carbon, nitrogen, and so on, right? So that's basically the trend as you go from left to right of any period, all right? What about going down a group? Well, as you go down a group, and I think I have a diagram here in the PowerPoint which talks about that. As you go down any group, what's going to happen is you're adding a shell to the atom as you go down the group. The shell that is added will be larger in size, and therefore, because the size is defined by the distance between the nucleus and the valence shell, the outermost shell, the atomic size will increase. I think I have a diagram here which, or I thought I did. Hold on. Okay, I thought I did. Okay, let me, again, my poor artistic skills might not do justice to this. I'm going to try anyway. So let's take group 1, right? So in the case of group 1, you have the first element would be hydrogen, followed by lithium, followed by sodium, followed by potassium. I'm going to stop there, but you could continue to rubidium and so on. In the case of hydrogen, right, the first shell is the only shell in the case of hydrogen, which has 1 electron. However, in the case of lithium, you're going to have the first shell, which would have 2 electrons, and then the second shell, which would have 1 electron, right? And then when you get to sodium, first shell will have 2 electrons, the next shell will have 8 electrons, and then the third shell will have 1 electron. And then when we get to potassium, that's even a larger atom because the first shell will have 2 electrons, the second shell will have 8 electrons, the third shell will have 8 electrons as well. And then the fourth and final shell will have 1 electron, right? So you can clearly see that as you go from hydrogen all the way down to potassium, the distance between the valence shell or the valence electron and the nucleus will increase, right? So therefore, the atomic size will increase as you go down group 1. And that is true for all the groups. As you go down any group, the atomic size will increase, all right? So just to recap, going from left to right of any period, the atomic size decreases because as you go from left to right, you're adding a proton to the nucleus, you're adding an electron to the valence shell, the nucleus will have a greater pull on the surrounding electrons, and therefore the atomic size will decrease as you go from left to right. On the other hand, going down any group, the atomic size will increase because as you go down the group, the distance between the valence electron and the nucleus will increase because the valence electron will be in a higher shell, and therefore the atomic size will increase going down in the group. So, with that said, let's look at the question. This question here in part B, number 1, says you're to rank the following elements by increasing atomic radius. In other words, you're starting from the smallest to the largest, right? You're given carbon, aluminum, oxygen, and potassium, all right? So, of these 4, let me see here. Carbon, oxygen, aluminum, where's aluminum? Oh, okay, aluminum there, and potassium. Okay, good. So of these four, which one would you expect to be the smallest in size? Between carbon, oxygen, aluminum, and potassium.
Oxygen.
I would expect oxygen to be the smallest because oxygen is to the left. I'm sorry, oxygen is to the right of carbon, right? And in the same period. And aluminum is where? Oh, aluminum is in the group in the period below. So you'd expect that to be largest. So oxygen will be the smallest, followed by what?
Carbon.
Followed by carbon, followed by
Aluminum.
aluminum, and then potassium. Okay, very good. Right. So this will be the order in terms of increasing atomic radius. All right. Okay. Now that's as far as atomic size is concerned. Now, another property that we can look at in terms of trends in the periodic table is what is called electronegativity. Now, let me first define what we mean by electronegativity.
It's on the bottom, bigger.
Electronegativity is the ability of an atom to attract shared electrons. All right? That's what electronegativity is. So if you have two atoms bonded to each other, right? The one that has a greater attraction for the electrons shared between them would be the more electronegative element, right? And there is a table in Canvas, the same chart, the same packet that I've provided for you guys. Let me just show you what that looks like. We go here, here.
And also one about the ionization.
Yeah, we're gonna talk about that, yeah. Okay, so. I think it's the very last page. Yes, this is it, right? Now, a guy by the name of Linus Pauling, Nobel Prize winner in both chemistry, and I think he got a Peace Prize as well. Anyway, did a lot of work, and one of the things that he is known for is what you're looking at here. Basically, what he did was that he used some thermodynamic data to develop a scale for electronegativity, right? So he developed a 4-point scale, right? And based on some thermodynamic data, he came up with numbers to represent the magnitude of the element's electronegativity. And this is what he came up with. In different textbooks, you're going to see some different versions with some slightly different numbers. So we're going to stick to using this particular table whenever it comes to determining the electronegativity of different elements. So as you can see here, fluorine is the most electronegative element that there is, right? It has a maximum value of 4.0. Now, what you'll find is that if you go from left to right of any period, the electronegativity increases. As you can see, for example, going back to period 2, the electronegativity increases as you go from left to right. The same is true for period 3, and pretty much all the periods, with some slight exceptions, right? But for the most part, that's what you find. As you go from left to right of any period, the electronegativity increases. And what you'll find also is that as you go from top to bottom of any group, the electronegativity decreases. And again, there are some exceptions, slight exceptions, but that's pretty much what you'll observe. So with that said, going back to the question, it says rank the following elements by increasing electronegativity. And it gives you the elements sulfur, oxygen, neon, and aluminum. All right. So, oh, by the way, you'll notice going back to the table, I should have mentioned this. you'll notice that there are no group 8 elements. Oh gosh, where is that? Okay, you'll notice that the group 8 elements are not included, right? And that's because basically they are considered to be inert and therefore will have little tendency to attract electrons, right? To themselves. So therefore, basically we can say that the electronegativity of group 8 elements is 0, right? Okay, so with that said, let's go back to the question. Rank the following elements by increasing electronegativity. So remember what I said, going from left to right, the electronegativity will increase. Going from top to bottom, the electronegativity will decrease. Okay, so of these here, and remember it says increasing electronegativity. So you're starting from the smallest, right? So I would say that neon will be the first one because neon, as I said before, has very little tendency to attract electrons to itself. So I'll put neon here, right? Now, my question to you is, what would be the next element in terms of increasing electronegativity? Let me see. We have sulfur, we have oxygen, and we have aluminum.
Aluminum.
Aluminum, I would agree with you there. Okay. And then what?
Sulfur.
Then sulfur. And then
Oxygen.
oxygen. So sulfur and then oxygen. And that will be it. All right. Okay. Any questions about this? Any questions? Okay, the next question is asking, what is the difference between electronegativity and ionization energy? So I gave you the definition of electronegativity already, right? It's the tendency of an atom to attract electrons to itself, or I should say attract shared electrons to itself, right? Now the ionization energy, let me give you that definition here. Okay, this first. So the ionization energy is, so this is ionization energy. Energy required to remove an electron from a gaseous atom, right? So in other words, if you have an atom X in a gaseous state and you remove an electron to form the gaseous ion, right? Then the energy required for this is the ionization energy, all right? So that's the difference between electronegativity and ionization energy. Electronegativity is the ability of an atom to attract shared electrons to itself, while the ionization energy is the energy required to remove an electron from a gaseous atom. And in the videos, I discussed the trends when it comes to going across a period and going down a group. So let me just recap that particular discussion. If you remember, I said going across a group, the atomic size decreases, right? What that means is that the distance between the valence electron and the nucleus will decrease, right? And that's because the protons in the nucleus will have a greater hold on the surrounding electrons. So what does that mean in terms of the energy required to remove that valence electron? It means that that electron, as you go from left to right of the pair, will become more difficult to remove, and therefore more energy will be required. So therefore, what you'll find, generally, there's some exceptions again, but generally speaking, as you go from left to right of any period, the ionization energy will increase, all right? The opposite will happen if you're going down any group. If you're going down any group, the distance between the valence electron and the nucleus will increase. So therefore, the nucleus will have a lesser hold on the electron as you go down the group. So therefore, it's easier, it becomes progressively easier to remove that electron as you go down the group. So that's what you'll find. What you'll find is that the ionization energy will decrease down any group. All right. So, all right. So with that said, let me clear this and scroll down. Oh, okay. So number 4 says, why does fluorine have a higher ionization energy than iodine? So we go to the periodic table, we look at where fluorine is, we look at where iodine is, And what do you notice? You notice that fluorine is at the top of that group, and iodine is below, right? So how would you answer that question? Why is it that fluorine will have a higher ionization energy compared to iodine? Because,
Fluorine is higher than Earth
and therefore,
as it requires higher, yeah.
well, let's talk about what happens in terms of the distance of the electrons. So, so in other words, why is it that fluorine has a higher ionization energy? Why is it compared to iodine? It's harder to remove the electron from fluorine.
The stronger the electronic attraction.
Exactly, there will be a stronger attraction between the valence electron and the nucleus because the electron is closer to the nucleus. In the case of fluorine, in the case of iodine, it's further away. So therefore, it is easier to remove the electron from the fluorine atom compared to the iodine, or conversely, it's harder to remove the electron from the fluorine compared to the iodine. So therefore, that's the reason why fluorine has a higher ionization energy compared to iodine.
Was it harder to get?
I'm sorry.
Was it harder to get?
Because in the case of fluorine, it's a smaller atom. The valence electron is closer to the nucleus.
Okay.
So therefore, there's a stronger attraction between the valence electron and nucleus. And therefore, it's harder to remove the electron from the atom compared to iodine. Okay. And then we get to number 5, which says, why do elements in the same family generally have the same properties or similar properties? And the answer is what? And when I say same family, they mean the same group. Why do elements belonging to the same group have similar properties? What do you think they have in common? So let's take let's take group 2. What do they have in common in terms of their atomic structure?
They all have 2 valence electrons.
They have 2 valence electrons, exactly. And basically, when it comes to chemical properties, it's the valence electrons for elements that determine their chemical properties. So the answer for number 5 is that elements in the same group has the same number of valence electrons and therefore will behave chemically the same way or similar way. Right? Elements in the same group will have the same number of valence electrons, which basically cause them to behave chemically the same way. All right? Okay, and I think that's it for this assignment. So what I'm going to do now is open up a Dropbox for assignment number 11. So let me go here. Okay, so I'm going to set the deadline as Thursday. Yeah, Thursday. Enough time for you. Okay, so let me do this. So there. This is Thursday. And see. All right, so now it's Dropbox available for you to submit your assignment number 11. Yes, sir.
I have like questions. Party theory, or is it three not or is it what's the way
Okay, so electronegativity is the ability of an atom to attract shared electrons to itself, right? Ionization energy is the energy required to remove an electron from a gaseous atom. All right, so also let me, before I forget, let me publish the videos for chapter 12, which is the next chapter. So yeah, take care. Make sure you watch those videos. All right, so it's now published. So make sure you watch those videos in preparation for next class, all right?
Yes,
All right. Yes, sir.
So. So for part D, how would you title how many shell, or how many, electrons are in each shell? So. Is it with one column down, it's.
Okay. So you're talking about here, right?
Yes.
Okay. So what you have to remember is that the first shell will only have a 1s sublevel, right? The second shell will have 2s and 2p sublevels, right? Now, remember, the s sublevel only has one orbital.
Yeah.
The p sublevel will have 3 orbitals, right? Each orbital will have a maximum of 2 electrons. So in the first shell, you have a 1s sublevel, the maximum capacity is 2. In the second subshell, you have the 1s and you have the 3 2p orbitals. So that's 2 in the 2s sublevel, 6 in this 2p sublevel. So the maximum is 8, right? In the third sublevel, you're gonna have 3s, 3p, and 3d. All right. The D sublevel will have a maximum of 10. All right. So therefore, the maximum number of electrons in the 3D sublevel will be 2 from the S, 6 from the P's, and 10 from the D. So that will be a total of 18.
So be 18.
Exactly right.
Got it.
And so on and so forth. Right.
The D is because there's 5 volts D.
Yeah, right. There are 5, yeah. The D sublevels, the D orbitals, they come in sets of 5. And each of them will have a maximum of 3 electrons. So therefore, the total capacity is 10. For the D sublevel.
So we probably won't be getting questioned on like, what is it, FR?
Yeah, at this level, yeah. For Chem 1, we get into the heavier one, but yeah, I'll go easy on you guys.
You were like, don't think about the six over.
Yeah, so don't worry about those heavier elements.
So. You said about for abbreviated.
Okay, yeah.
Where, like, I wasn't understanding how we were getting like the helium
Well,
abbreviation.
if your element, let's say for example, the element that you're trying to write, the electronic configuration abbreviated, let's say it's nitrogen, right? Nitrogen would have an electronic configuration of what? 1s2, 2s2, 2p3, right? So what you do is look for the group 8 element that comes before nitrogen, which would be helium, right? So nitrogen is here, right?
Okay.
And helium is here, right? So therefore, helium has an electronic configuration of 1s2, right? So I would replace that 1s2 that is present in the electronic configuration of nitrogen with the symbol of helium in square parentheses. And then I'll write down the rest of it. So therefore, in the case of nitrogen, it would be the helium symbol, then 2s2, 2s3. I mean 2s2, 2p3.
One more time, why are we going from, like, why are we getting the helium?
That's basically the rule that is set up for writing down the you have to look for the group 8 element that comes before the element that you're trying to write down the abbreviated version. Group
Okay.
8.
8.
Yeah. So like for example, if you want to do this, then you have to look for the electronic configuration of neon within the structure.
So if it were like BR would be AR?
Exactly.
Okay, so you just at the very right.
Exactly. If you want to do this, then you have to identify that.
Okay, that's
Exactly. So it's a group 8 element that comes before the element that you're trying to.
Okay, yeah, that's easier to understand.
Right, exactly.
Okay.
Yeah.